Okay, not good enough. So, this is the standard deviation for NPQ problems, or binomial problem. I call them NPQ because those are the most important things to figure out is NP and Q. Square root of NPQ, so it'd be square root of 44 times 0.152, 0.848. Some of you guys might realize that you just did N times P. So you just multiply that by Q and then take a square root. So it's a quicker way to do it in the calculator. All right? So somebody help me out.
2.38.
2.38? 1.4. 1? Okay. So remember, a standard deviation, no matter where the hell it came from, you got to go at least 3 places. Cool. All right. Now this last, how are we doing so far? Any questions on what we've done so far? These are the exact kind of questions that I love to ask. This is a very good hint of a handout. Especially this last dude. Anybody remember what we called unusual? I did discuss this a little bit once, but now it's going to become a lot more important. In a normal distribution, what percentage of the data is within 2 standard deviations? If I go 2 standard deviations out from the mean, 95%. That came from where? Empirical rule. I love it. David's like, it came from my head. What do you want from me? So what percentage is outside, is more than 2 standard deviations away from the mean? 5%. Even if I had to use chubby dude. Chubby dude said within 2 standard deviations there's 75% of the data. So it means there's only 25% of the data outside. So we've decided to call anything outside of 2 standard deviations, so I'm going to call that unusual. It sort of goes back to the question, remember you had to do those stem and leaves and you had to identify the outlier? And I promised you I would eventually make a more detailed explanation of what an outlier is. We just did. Right now we're calling anything more than 2 steps away, 2 standard deviations away. Anything more than that is unusual. So how do I answer this question? Would it be unusual to find 17 out of 44? Yeah, so what do I put right in the middle? Yeah, so this feels very familiar, right? I kind of got you ready for this by asking that question over and over again. But now I'm going to go 2 steps out. So I go 6.66, oh yeah, 6.688. So what's 2 standard deviations down? So just subtract 2 of these. So you can do 6.688 minus 2 of these.
4.307. 1.9.
One more time. Yeah. 1.9. 26. Let me stop there for a second. Is everybody put in the idea with the concrete? I want to take 2 steps down, so I just subtract 2 steps, standard deviations from the mean. And now do the same thing, but now I'm just going to add. Add 2 steps. 11.45. So would it have been usual to find 17? Yes. So this is neat. This is our first little entrance into ways of gauging if something unusual happened. So if I'm somewhere and I pick 44 randomly selected people and I'm in a certain part of downtown and I pick 44 people and I find 17 of them, I might go, where am I? Is there something special about where I am? Am I right outside of a smoke shop? Where am I? You kind of see what I'm saying? Would there be am I in a place where I would expect to get more smokers, or was that just a random occurrence? So unusual, does that mean that it's impossible for that to happen? No. Just like if I flipped a coin 500 times, is it impossible to get 490 heads? No. Is it unusual to get 490 heads? Yes, I like it. So you get the idea there. So unusual doesn't mean impossible. It doesn't mean when you see it, you go, oh my God. It just means you see it and you go, that's interesting. All right, 490 heads, really? Is that what you did in your weekend? Okay. So would this be unusual? Definitely. It's way outside of the expected. It's way out there, so that's why. So if I said, would 7 be unusual? No. Would 10 be unusual? No. That's inside the expected, right? Or let me say it like this, the min and the max usual values are those. Maybe. So you might see some homework questions that use this language. So real quick, since I just said something about it, remember a while back we did something like, we actually did what we're doing right now. You just didn't realize it at the time. So if I flip a fair coin, and I'm looking for heads, what's the probability of success? 50%. I love it. So if I flip a coin 500 times, bless you, the probability of success and failure are both 50%, right? How many do I expect? How many heads do I expect? Yeah, it'll be 0.5 times 500, 250. So before we had trouble identifying, well, would 300 be unusual? Or would 270 be unusual? Where's that line for where unusual starts? We actually had this discussion earlier this semester. You guys are like, I could barely remember yesterday. So now we have a way of determining a little more specifically where that is. So if I say, well, so what's the standard deviation in this problem? Standard deviation formula is square root of NPQ.
250 times.
I like it. NP is 250. Q is 0.5. So it's going to be like 11 point something. 11 point. 180?
Yeah.
All right, I like it. So you're like, dude, what do you want? All right. 180. Say that and I'll be happy. So 11.180. So we can do like we just did. So if I start at the mean, which is 250, and then go up 2 of these, the most heads I would expect out of 500 flips would be how many? Well, 250 plus 22 point whatever. So it'll be 272.36. Does everybody see where that number came from? I started at 250 and I took 2 steps up. And how big is each step? This big. So I did 250 plus 2 of these. And then if I want to know what, if I go down, so it'll be 250 minus 2 of these. What do you get? So I really want you to understand, we're not at the point yet where I can do a full analysis of a claim. But if somebody said, I think your coin is weighted to favor heads, and I'm like, you're screwy, what the hell? And you're like, no, I flipped it, you flip it 500 times, and I got 300 heads. Is that evidence that something weird is happening? Yes, it is. It is evidence. Is it strong evidence? We can't say yet. That's going to have to come later. But right now, we got a very fundamental kind of basic tool of analyzing a claim. I think the coin, if it was fair, I would expect at most around this many. Is it impossible to get more than this? Of course not. But is it unlikely to get more than this? Yes. So if I do see more than that, that's evidence that maybe something happened. Especially if I give the coin to somebody else and they flip it and they get like 312 heads. That's even more evidence. Because I repeated the experiment. Are you guys kind of with me? So later this semester we'll start to really get into the process to test claims, the full steps we got to take. But this is a very quick, rough and dirty example of how to even see if there's a claim to investigate. So yeah, we got evidence. We should look further into this. If that coin came up twice, especially above 300, it's way up there in unusual territory. I like it. Maybe. Okay, so the formulas, now of course on the day of the review we'll go over all the formulas, but if you want to add some to your formula sheets right now, you can add these two obviously. And I don't know if I put it down here in its weird form. Yes, I did. And that one, of course, the probability, the binomial probability. Okay. Yeah. So 4.3 is all about binomial probability. I think I'm going to, in the interest of catching up, let me see if I did. Yeah. I'm going to go ahead and make 4.4 extra credit. The more you understand binomial, the easier 4.4 should be. There's only a few questions, but you'll see, if you want to try it out, you'll see what I mean. It's not that hard, but just so we have some time to catch up. So 4-4 extra credit. You don't have to do it. If you don't do 4-4 homework, it won't hurt you. If you try it out, if you get enough of it right, you'll get some extra credit added to your homework grade. Because I really want to get into chapter 5. Of course you do, Jeff. Anything lingering from chapter 4 that you want to talk about before I get into 5? I love some of you guys are like, yeah, dude, everything. All right, well, come see me then. All right, so let me ask you this. I don't know if you noticed the title to chapter 4, but the title to chapter 4 is called Discrete Random Variables. Somebody remind me what discrete means. Discrete versus continuous, because the next section is continuous random variables. So what did discrete mean versus continuous? Who remembers?
Discrete would be like a whole number, like
could be.
And then like continuous would be
Yes. So continuous means the variable could take any value between 0 and something or whatever within a continuum. It could take any value on. Right? So the weight of your backpack could be anywhere from 0 up to whatever the max is for the backpack to carry, right? And it could be anything in there. It doesn't have to be 11 pounds. It could actually be 10.9344. So it's possible for the value to be anything. But if I said how many doors are on your car, can it take any value on? No. In that case, it is whole numbers. You got 1 door, 2 doors, 3 doors. Hopefully you got 0 doors. You just have to be born in it to drive it. I don't know what that means. You just have to exist in it. I don't know. Motorcycle, sure, I like it. That's the other way to go, thank you. It's just open to the world, Jeff. So what we're getting into now is continuous variables. So what does that mean? That means that my variable can take on any value. So that gets a little bit different. Okay. Let me see if they give me a nice example. So the very first type we're going to look at is easier than it seems at first. It's called a uniform distribution. I don't know if you guys know what that word uniform means beyond some kind of a costume or something. Uniformly distributed means that everybody gets the same amount. Right? To distribute something uniformly, everybody gets the same amount. So it's, if I drew this, let's say I had a variable uniformly distributed from 0 to 5. So from 0 to 5 is uniformly distributed. So which means I could draw it and I can make it look like this. So every possible number, it's continuous variable. So we're in continuous variables now. So it can take on any value in there, but they all have the same probability. So I really want you to remember, when you made histograms, how tall were the rectangles? What governed how tall the rectangles would be? Yeah, the relative frequency. And what's another name for relative frequency? Percentage. And percentage really is just probability, right? So the height of this is going to be the probability of each thing. Well, if it goes from 0 to 5, what should the whole thing be? All the probabilities should add up to be 1. I like it. So how tall should it be in order for that to be true? I want the area of this to be 1. So how tall should it be then?
0.20.
Yeah, you take 5 times what to be 1? 5 times 0.2 is 1. Or you can just do 1 divided by 5, 1/5, right, which is 0.2. Let me stop there for a second. So we're making the connection now between areas and probabilities. And why does it make sense that those should be related? Well, I can talk about, a problem like a bullseye problem, where you're throwing darts at it, and the larger the area is, the more chance there is for me to get it there. The higher the probability is. So if I'm just randomly throwing it there, and then somehow the probability I hit it somewhere is related to the area of that area of that region. You guys kind of with me there? So area seems to be related, but this is more of a mathematical idea here. What other way can I do this? Well, let's try some problems out. So if I wanted to know the probability that x was from 1 to 3, and now I understand that the probability, if I draw it like this, the probability is equal to the area. So when I want to answer a question, a specific question, I just have to find the area that this question relates to. So how do I find an area? Well, it'd be from 1 to 3. So what's this area? Well, how wide is it?
3/5.
Yeah, so it's 2 wide times 1/5 tall is 2/5. So it's a 2/5 chance. So uniform probabilities, even if they don't give you the height, it's easy to find the height. You do 1 divided by how wide it is. That's got to be what the height is, because overall it's got to be 1. So we're not going to do stuff like, you could have, this is a uniform distribution. You could actually have triangular distributions. You can have any shape you can imagine, right? So if I want to know the probability from this to this, I would find the area of that triangle. You guys kind of with me? So this is nice. Uniform means I'm finding areas of rectangles. Kick ass. Those are nice. How you guys doing so far? We're not going to do this, by the way. Don't freak out. Right? I don't know if some of you guys look at that and think about Vegas, but I mean, so what about this? This is coming up in our future. Is the normal distribution? Does it have a geometric shape that I'm used to? No. It's not triangular. It's not rectangular. It's something freaky as hell. And what we're going to do is, when we get to this point, I still want to find the area. So if I want to know the probability it was between this and this, I still want to know the area of that. We're not going to calculate that by finding areas, because I don't know if some of you guys know, that's what calculus does. I'm not going to teach you calculus. Calculus is all about, well, two things, but the second thing is finding areas under freaky-ass curves. Geometry is great with triangles and rectangles and polyhedrons and, whatever. Calculus says I can handle any freaky curve, right? What we're going to do is we're going to use a chart of values that people have created for us, thank God, right? We're basically going to beef up empirical rule. Because the only stuff we know about empirical rule is within 1, within 2, within 3. Now I want to know stuff like in between negative 1.9 and negative 1.27. What's the area between those two? Oh shit, empirical rule doesn't do us any good. You guys semi with me here a little bit. So that's in our future, right? So right now I'm trying to lay the groundwork of explaining why area equals probability, why that makes sense. Maybe. Let me see what other kind of weirdness they throw at you. Oh, cool. A couple little things. They give you, I'm not going to make you memorize these, obviously, but they give you the formula for the mean. What do you think the mean of this would be? What's your gut tell you the mean? What's the expected value? 2.5. Yeah, exactly. So if I had a lot of people just randomly pick numbers from 0 to 5, I'd expect to get an average of 2.5. Does that make sense? I like it. So the mean is 2.5, and that really is just, let me make this more general. So if I had a uniform distribution from A to B, let's say this is, let's call it P for probability. the mean would be A plus B divided by 2. That's pretty much what we just did, right? Everything's equally weighted, so the mean should just be the average of the high and the low. Now, let me let that sink in. What about standard deviation? This is where things get weird. They get so weird, I don't even know the formula, but I'm not going to make you memorize the thing. Oh, here it is. Cool. Yeah. Now, I don't know. Try to imagine. Just start to imagine the math that would go into figuring out the standard deviation of this general shape. Right? The standard deviation. So I love it. Last semester I taught this. We're not going to get into the math behind this. I think last semester I brought in the proof of this, and I just showed it really quickly because I had so many people come up and say, "Where'd the 12 come from? Where'd the 12 come from?" It comes from the math. It just comes from the math. So you have to excuse me for today because I had to answer like that. I don't know if you guys realize that my life has been trying to get the quiz done and ready for you. So I basically didn't do anything to get ready for today. But I'm going to see if I can't find where I put that proof. I'm just going to show it to you real quick. It's nothing you have to know. Just to show you, in case anyone's curious, where did the 12 come from? I can show you where the hell the 12 came from in the work. Okay. So for example, for this one, what would the standard deviation be? How do I set this up? What's B and what's A? B is 5. A is 0. Right? Sorry, this was a specific problem, right? Going from 0 to 5 divided by the 12. So somebody help me out. That would be 5 over 3 point something. So 1.4. Is it really? 1.4. 43. Okay. Let me stop there for a second. And that's just using a formula. We don't know where that formula came from yet. I'm going to show you, right? Because I really don't like showing you formulas and not showing you where they came from. It's not a very often used formula, so it's not going to be a huge part of what we do. But still, you should see where it came from. Can somebody help me out? Would it be unusual to get 4.3? Is 4.3 unusual? How would you figure that out? I like it. So the mean was 2.5. Standard deviation was 1.443. So how far do you have to go up? 2 steps. So 2.5 plus 2.8. Roughly, right? 2.88. Yeah, 5.38, whatever. And then down, I don't really care about, because 4.3, is that unusual? No, it's in there. Let me stop there for a second. So that idea of what unusual is can be used on a lot of different distributions, right? If I know the mean and I know the standard deviation, I can figure out what's unusual, what's not unusual. Every time I say that, I think of it's not unusual. Thank you. All right. I won't sing because that's horrible. I don't want to scare you guys away. I want the stats to scare you, not my singing. Okay. Oh. Yep. Oh yeah, that's right. Oh cool. So we're right where we need to be. Good, good, good. Okay. I'm sorry. I'm just making sure. All the stuff I normally do, I'm doing right now. I'm doing it live. Thank you. All right. So So often in math we have a process for something that doesn't care about what the values are, what the numbers are, whatever. Right? That's what I'm trying to teach my 90 students is I don't care that it's X and Y. You still add them to get the total. It doesn't, it doesn't care that we don't know. So it doesn't care where the mean and standard deviation came from. I can do this, just like I just said, to figure out what unusual or not unusual is. All right. So we only do those 2 sections. If you're worried about the fact that the next test covers several chapters, chapter 5 and 6 were 1 chapter in the old book, right? In the book I used to use. So I mean, they really broke it apart in this book, which is fine. So don't freak out too much about that. So. Let me see if there's anything freaky in here. Oh, before I get too far, I always forget about this. This book loves to use this notation like they ask you X is like what? And they for binomial distribution, they'll want N and P, right? So I don't know if you've noticed that. In the homework, they'll ask you X is what? And you're like, what?
Well, they don't even, in one of the problems, they don't even give you that. They just ask you what the distribution of X is.
There you go. Okay, so you got to realize they want that notation, and this notation is not used almost beyond this book, basically. Right. So it's just this book. And I always forget they do this. It's really hard to assign problems that don't ask this question. So I might as well talk. So if I had a uniform distribution, what do you think they put here? No way. And then they got to tell me. What do you think they got to tell me for that? Let me see if I remember that's right. So what's important to know about a uniform distribution? Let's see if they did it correctly. I'm going to remind myself. What should be important is A and B. Everything comes off of those. If I tell you that A is 1 and B is 7, then I know that's 6, so then how tall would it be? 1/6, right? Everything comes off of those. So it should be, I just wanted to make sure that they agree with me. But I'm not finding an example very quickly.
Are you looking for one that uses
U.
that?
Yes.
I believe it's 4.3. Oh, no. Just kidding. Sorry, YouTube.
That's all right. Shoot, I can't find it. But it should be A, B. That's what makes sense to me. When we get to normal distributions, what's going to be important is the mean and the standard deviation. That kind of makes sense, right? And you know the mean and the standard deviation for a normal distribution. Because then I can do z-scores and all that kind of stuff. Does that sound familiar? So that's going to kind of come back up. It does kind of suck. I tried one semester to teach probability first. Because probability sort of just is in the middle of everything. It's its own little thing. And then we got to come back to z-scores. And you're like, oh yeah, z-scores, I remember that. It didn't go so well that semester though, so I decided not to try that again. But anyway, that's coming back up. And it makes sense that we're going to go back to these two. Okay, so just in case you see questions like this, what distribution is it? Or they got this x with a little approximated by. They want like B for binomial and P, U for uniform, so forth. Okay, cool. Now, the next thing that I wanted to do, kind of sucks that I didn't have time to get ready, is I need to make a connection between the binomial stuff and the normal, because then it really makes a lot of sense. So help me out here. We're going to do this. We're going to manage this. Say I flipped a coin 14 times. What's the average number of heads I would get? Yeah, exactly. So that's 7. It just makes sense. And of course, using the formula, it'd be n times p, so it'd be 14 times 0.5, 7. So we already know that the probability of success, the probability of getting ahead would be 5%, 50%, 0.5, and Q would be 50%, probably getting a tail. All right, so that's all nice. So I want to use this example because it's relatively easy. We have it in our heads. Can somebody tell me exactly what the probability of 7 heads is? So we know that it should be around the most likely thing. The probability should be around the highest. All right, so how do I figure out what the probability of exactly 7 is? How do I do that? This should sound very familiar. The probability of exactly 7 heads if I flip a coin 14 times. How do I get that probability? What do I have already? I have N is 14. I have P and Q are 0.5. So what formula do I use?
14C7.
Yes, this is a binomial situation here, right? How many outcomes could there be? 2. Heads, tails. Binomial. Okay, cool. I'm doing a certain number of trials. Probability of success, probability of failure. So what would that formula look like? You started saying it, Dean.
14C7.
Yeah, 14 through 7.
Times 0.5, 7 times 0.5, 7.
I like it. Somebody might realize that when P and Q are 0.5, this is always going to be 0.5 to the n, because that's 0.5 to the 14th, right? We add powers. But you don't have to know all that. It's just nice algebra. Just plug all that stuff in there. So somebody help me out. Plug that in your calculator if you have a calculator.
2095.
All right, how we doing? Is that cool? Is that right?